In this lesson 1.5, we're going to deal with what are called complex numbers. And as we start it, we'll take a look at the objectives. Add and subtract complex numbers, divide complex numbers, multiply complex numbers, simplify square roots of negative numbers, and the imaginary unit I and its properties, and using complex numbers to solve applications involving electrical engineering. And as usual, take a moment, pause, read this over. Now, when mathematicians were working with things, they sometimes got something that looked like this: the square root of -4. Now, there are no two numbers that if you multiplied them together give you a negative. If you multiplied two negatives, that would give you a positive. If you multiplied two positives, that would give you a positive. So they came up with something to try to work with this, and that was to develop this concept of something that's called the square root of -1. Now, they will define that in this section and then throughout the course as the letter I. So the square root of -1 is I. So watch what we do here. The square root of -1 squared, which would be in a sense I squared. This is -1. And we had said if our index number is 2, this is 2 over 2, which is 1. We just take away the radical side, and this is equal to a -1. So throughout this now, anytime we have this I squared, that will equal -1. And that's what they're referring to down here. Now, they've called this an imaginary number. It's imaginary because that's what they first called it, but it is, in a sense, a number. It's not imaginary, but we call it the imaginary number. Now, as we go into some examples, we're calling this example 1. It's in 4 parts. I'm going to go to the whiteboard to work these out for you. And again, suggest you take some good notes. Now, this, when we see the square root of a negative value, we know that's not a real number because, again, no two numbers exactly the same multiplied are going to give you a negative. Two negatives give you a positive. Two positives give you a positive. So what the mathematicians did, they're going to take this and divide it, in a sense, into the square root of -1 and the square root of 16. And we know that is true from properties of radicals. Now, what did we say was the square root of -1? Well, this was I. And then the square root of 16 is 4. But they usually write the I after the value, so 4I. The I usually comes at the end of what you're dealing with as the proper protocol for listing that. Now, for this one, again, we'll take out the I. That's the square root of -1. Now we have the square root of 4 times the square root of 2, and we're simplifying this. What is the square root of 4? 2. 2, the square root of 2, and then the I would be the simplification of this. Now, this one is something you'll often get is various powers of I. So let's give you the background. We know that I equals I. We know that I squared equals negative 1. Now, what does I to the third equal? Well, we know it equals I squared times I. Well, I is I, and I squared is negative 1. So I to the third power equals negative I. Let's go over that again. So I equals I squared equals negative 1. So dividing I to the third into I to the second times I to the first, in a sense, this is I, this is negative 1. So we don't write negative 1I, we just write negative I. And for this one, we did that one earlier. For squaring this, it's just going to become I squared, because negative times negative will give you a positive. I squared is negative 1. All right, let's go back to the whiteboard, or from the whiteboard, and I'll clear this up so you can see all of the answers. Again, you can pause and look this over. Now in example 2, as we look at it, we actually see what I did here earlier, but there is a protocol. This is your basic pattern, and if you go I to the fifth, that would be I to the fourth times I. Now I to the fourth, we said, was 1. So 1 times I is I. So then I to the sixth is I to the fourth times I to the second. I to the fourth is 1. I to the second is negative 1. So this is negative 1. And that pattern continues. So the key for doing any of these, as we look at this first one, A, which is I to the ninth, can you see this is going to be I to the fourth times I to the fourth times I. I'm taking that exponent 9 and dividing it into 4 multiples of 4. Well, this is I to the eighth times I, and any fourth multiple, as we see here, of exponents, this is just going to be a 1. So 1 times I, this is going to be I, which is what they show here. All right, let me clear this up. Keep in mind if you're taking notes. Now, as we look at this next one, we get I to the 28th. Now, this would be I to how many powers of 4? Let's do it that way. I to the fourth times 7. Can you see this would be, using the powers rule, this would be equal to I to the 28th power? But what is this? I to the fourth is 1. 1 to the 7th power is 1. And that's what they're showing. Now, as we go, there is a little protocol to this. In letter C, it's I to the 102. Well, can you see this would be equal to I to the fourth power raised to the 25th. This would give you 100 times I to the second. So this would give you a total of 102. This is 100 plus 2. Well, this is 1 to the 25th. That's 1. I to the second is negative 1. So all of this is negative 1. And that's what they're showing. So once you sort of understand this sequence, that every fourth power of I is a 1, you kind of think of it that way. Let's go on. Again, pause to read this. Now, we know from earlier lessons we have real numbers. These are all, and they usually thicken that a little bit. These are all the numbers that are on the number line. But this other group, now that we've introduced imaginary numbers, creates a bigger group than real numbers. And these are called complex numbers. Now, complex numbers have a certain way to write them. And the formal way of writing it is A, which is the real number part, plus BI, which is the imaginary number part. Together, that makes up the complex numbers. Okay? And the proper way to write it, for instance, if you had a fraction, you might say you put it all over 2. No, you can't do it that way. The proper way to write it is you put the real number over 2 and the imaginary number over 2, not over a common denominator. Keep in mind. Again, pause, read this over. Now, when we are working with complex numbers, adding, subtracting, multiplying, dividing, there is a protocol to follow when we are simplifying complex expressions. That is, we never leave I squared as I squared. We always convert it to a -1 and then do whatever is needed. And we don't have fractions such that the denominator has an imaginary number in it. Okay, hopefully that's what you've picked up from reading this over. All right, example 3, and if you're taking good notes, write these out. Here, this is simple addition. So we can put our real numbers together, 4 and a -5. And then we have a plus 3i and a plus 7i. Real numbers, imaginary numbers. This is going to be a -1, and this is a plus 10i, and it's in the form a plus bi. And that's what they have here. So pretty straightforward. You think of the I as a regular variable, an X or a Y, except anytime you get I squared, you have to change it to a -1 and do what is needed. All right, let's do B. Now, as we look at it, we have a -2. Now, this is subtraction, so we're going to change this to a +5 and this to a -3i. So this is going to be -2 plus 5, and this will be a plus 3i minus 3i. Because of the negative there, we had to change both of these signs. Now we're just grouping like terms. This will be a 3 plus 0, and that's as far as you go on that. And I'll show you the learn slide. Moving it down, there is your 3. Now, in multiplying these binomials that are complex numbers, we FOIL it in the standard way. Our first gives you a -6. Our outers give you a positive 9i. Our inners give you a -4i. And our lasts give you a positive a 6i squared. Now, this is where the I squared comes in. Can't leave it as that. What is I squared? I squared is a negative 1. So this becomes positive 6 times negative 1 is a negative 6. So I'm going to erase this. I wanted you to see where it came from. This will become a negative 6 here. Now we collect like terms. Negative 6 and negative 6 is a negative 12. And then 9i minus 4i is a positive 5i. All right, let's check this. And there it is, negative 12 plus 5i. All right. Now in this next one, we're squaring a binomial. And we can use that shortcut method. Square this first term, that's 4. Multiply these two, it's going to be a negative, and then double it. This will be 6, doubling it's 12i. And then squaring this is going to be a positive 9i squared. But we can't leave the I squared. I squareds are negative 1. So this value here is going to become a negative 9. So I'll erase it and change it. Now we have 5 minus 9 is going to be a negative 5 and a negative 12i in its complex form. And let's just scroll down and check it out. Negative 5 minus 12i. And you see the protocol of getting there. Now for some background information, we're going to take a look at complex conjugates. You may recall when we have something a plus b and a minus b, this would be the product of the sum and difference of the same terms. We got, if you recall, the difference of squares. Now, if the b portion of this happens to be imaginary, this is going to be a very useful tool in simplifying complex numbers. And that introduces us to what is called the complex conjugate. What is the complex conjugate? Well, you just put an I here, and that is the complex conjugates. And then notice this is going to be I squared here, if you square this part. And what did we say I squared was? A negative 1. So this will make this positive. Let's see it in action. And if you're keeping numbers, this is example 4a. There's our fraction. It's not in simplified form because we have an imaginary number in the denominator. So to get rid of that, the protocol is we can multiply anything by 1. Doesn't change the value of the fraction, but our 1 that we're going to multiply it by is going to be the complex conjugate of our denominator. What do you think that is? Well, that's going to be 3 plus I. And the numerator then is 3 plus I. Because now this is a 1. All right, let's do our denominator first, because that's the easier part. 3 times 3 is 9. Negative I times positive I is a negative I squared. But what did we say I squared was? Negative 1. So the opposite of a negative 1 makes our denominator now 9 plus 1 is 10. Okay. So let's FOIL our numerator here. This is going to be outer, first I should say is 6. Outers plus 2i. Inners plus 9i. And then last is will be a 3i squared. Let's put it there. So a positive 3i squared. But I squared is a negative 1. So this is going to become a negative 3. Just hope you can see where that comes from here. Now we have 6 minus 3 is 3. And this is going to be plus 11i. Now, if you put your answer into the software this way, they're going to count it wrong. Why? Because it's not written in the proper form. It has to be written 3 over 10 plus 11i over 10. Now it's in the proper form, a plus bi. Okay, there's the work for this first example. And kind of an interesting thing here. This is something new to me. They're saying we can often leave the answer in this form. Again, some softwares will count that incorrect. But again, as you work your software, be sure you follow the protocol they will accept. Now, as we look at example B here, notice I put it so that the exponent is positive, just moving it down. Remember, there's a 1 there. We're taking this down to its denominator. The exponent becomes to the first power. There we are. So again, we want to get rid of that imaginary number in the denominator by using the complex conjugate, which will be 4 plus 3i. And again, the numerator, 4 plus 3i. Now remember, we're multiplying this fraction by 1. Doesn't change its value. So our numerator is going to be straightforward, 4 plus 3i. But what will the denominator become? Well, when we FOIL this, and I can do it over here, we'll get 16. Outers is plus 12i. Inners minus 12i. Remember, when you multiply conjugates, the inners cancel out. And you get a positive, negative 9i squared. That's going to become a positive 9 because this is negative 1 times negative 9 gives you a positive 9. 9 and 16 is 25. And if you separate it, it would look like that. Or they're saying you could possibly leave it over the 25. Let's take a look at it. Scroll down. Here they are separating them. And I'm not saying that, they're saying you got this, but to separate it, to put it in its proper complex number form, a plus bi. This is the way I have been taught to do it. Now, for letter C, we have 1 over I. So we're going to multiply this by I over I. This gives us, for the denominator, I squared. I on the numerator. I squared is a negative 1, so this is I over negative 1, which is a negative I. All right, that was pretty straightforward. Let's check it out down below. negative I. Okay, not too many more to go. We're almost finished. Here we have some background information. Pause, take a moment to read it over. Now, normally when we're dealing with radicals and we have a times the square root of a times the square root of b, we can think of that as the square root of ab. But when we are dealing with imaginary numbers, and this is a negative a and a negative b, you don't multiply these two negatives together to get a positive. Imaginary numbers, this would not be true. How would you do that? Well, you would go I, the square root of a, times I, the square root of b, equals I squared, the square root, make a square root sign of AB. That's different. And what is I squared? I squared is negative 1, the square root of AB. So you need to be careful when you do that, and they're showing that down here. Now they're also given what is called a fallacious or a false proof that I want to show you so you could see it as part of our work. Again, that would be a fallacious proof. Not true. Again, if you're keeping numbers, this is example 5, and we are to square this. Now, the key here, I think, would be to convert this from this form into its imaginary form, which would be 2 minus I, the square root of 3, squared. That would be better. Now, squaring this, we get 4. Multiplying these two together, we get a negative. Double this, 4i, the square root of 3. And we can put that I there better, I think. Let's do that. And then we have to square this. Now, squaring this is going to be negative times negative would give us a positive I squared. And squaring the square root of 3 is 3. So I squared here is going to give you a negative 1 times 3. This will become a negative 3 here. So let's change that. Again, wanted to show you where it came from here. So what do we have? We have 4 minus 3, which is 1, minus 4, the square root of 3i. And let's check it out there. 1 minus 4, the square root of 3i. Now, they're showing another convention where instead of writing the I, when we are dealing with radicals, they sometimes allow you to write it 4i, the square root of 3. And why do they accept that? Because they want to be sure that that radical sign doesn't extend over this I. So this would be like the super proper way, but apparently they're saying this is an acceptable way. All right, one more to go. Now, for our last example, again, pausing to look at it, if this wasn't a negative under the radical, this would just be a 1. But let's simplify this a little bit. Square root of 4 is 2, and this denominator is 2i. So what is the conjugate of this? Well, a negative 2i. So a negative 2i. So this is a 1. So this numerator now becomes a negative 4i. Our denominator becomes a negative 4i squared. But we know I squared is a negative 1. So our denominator just becomes a positive 4. Let's erase that. Wanted you to see where it comes from. And now we can factor out a common 4 here. And this just leaves us with negative I as our final answer. And let's just scroll that down here. And there you see it. Okay, hopefully helpful, and let's wrap it up.